Hello, in this video we're in the weighted least squares regression setting, and we're going to look at a little bit of estimability and the blue, which is best linear unbiased estimator. So as a reminder, the model that we're looking at is y is equal to x beta plus epsilon, but here epsilon has a variance covariance structure, so it's sigma squared v. V is known and it's positive definite. Now what is often done is we transform it to an equivalent model. So we pre-multiply by the inverse of the square root matrix of V. And I have a video called the square root matrix if you want to learn more about the square root matrix. And so if you pre-multiply by V to the minus 1/2, then we can just call this V, y star, call this x star, call this epsilon star. And then it's transformed into the standard multiple linear regression setting where the variance covariance structure is sigma squared I. The rank of x is less than or equal to k plus 1 because there's k plus 1 beta parameters here. Now the first theorem is if this function, linear combination of the betas, is estimable in model 1 if and only if it's estimable in model 2. And so to prove this, we have to go both ways. So we assume this is true and then show it's estimable in model 2, and then we go the other way. We assume it's estimable in model 2 and then show it's also estimable in model 1. So let's go this direction first. So let's assume this linear combination is estimable in model 1. Then from previous video 26 in this playlist and theorem 1, that this linear combination is estimable if and only if there exists a t such that this vector L is equal to t prime x, which means it's a linear combination of the rows of the design matrix. So we need to show that there exists, say, a t star such that this vector L can be represented as a linear combination of the rows of x star. And then this would imply that this linear combination of the betas is estimable in model 2. So L prime is t prime x because we're estimable in model 1. So then let's, in the middle of this, let's put the identity matrix, which is v to the 1/2, v to the minus 1/2. But then let's group this and group that. So this is x star, and this is just another vector. Let's call it t star. Well, then that shows that it's estimable, it's a linear combination of the rows of x star, which shows it's estimable in model 2. So next, let's assume that this linear combination is estimable in model 2. Then there exists a t star such that this vector L is this, t star prime x star. But note that this vector L, which because it's estimable in model 2 can be represented as t star prime x star. But this right here, by definition, is we've pre-multiplied x by the inverse of the square root matrix. But then this is, we can just think of this as a vector, call it t, and then x carries over. Well, that says it's a linear combination of the rows of x, which that implies that this linear combination is estimable in model 1. And then the theorem's proved. So the next theorem, estimators that are linear in y are also linear in y star. And vice versa. So meaning if it's linear in y star, it's also linear in y. So let's go this way. So let's assume it's linear in y. And then let's put the identity matrix in the middle here, which doesn't change it. But we're going to use the square root matrix and the inverse of the square root matrix. And then group them. This is what we were calling y star. And this is just another vector. And so that says it's linear in y star. So here, let's assume it's linear in, going the other way. Let's assume it's linear in y star. But y star has actually just been y pre-multiplied by the inverse of the square root matrix. But then this can be thought of as a vector, call it t, and then y carries over. Well, that shows it's linear in the y's. and then the proof is finished. So next theorem, if this linear combination of the betas is estimable in model 2, and beta hat is the weighted least squares estimator of beta, then this linear combination of the least squares estimates is the unique blue of this linear combination of the true betas. Blue is best linear unbiased estimator. And the proof of this, we actually have already proved this. So by previous video 26 in this playlist and theorems 2 and 3 in this video, aka the Gauss-Markov theorem, applied to model 2, that means it's the unique blue. So meaning that L prime beta hat is, and then since we're in model 2, the least squares estimate is this. But then when we expand everything, this can be thought of as AY. So when we expand it, so this is, the inverse of the square root matrix times X, same here, same here, same here. And then when you unfold all that, then it just simplifies to T prime AY. And remember, AY is the least squares estimate for beta in the weighted least squares regression setting. And this, because of theorems 2 and 3 in previous video 26 in this playlist, is the blue. But that says that that's equal to this, so that's the blue. And it has the smallest variance within the class of unbiased estimators that are linear in Y star. But from the previous video means it's also linear in Y, which here you can kind of see that it is. Where A is called the hat matrix, and see previous videos 50 and 51 in this playlist for more details about A and that hat matrix. Notice here that the T star is really the T is equal to T star V to the minus 1/2. So actually, when you unfold this, the V to the minus 1/2 here is actually brought into the T star, and we just call it T. That's what this is saying. But then the rest of this can be thought of as A, and then of course Y. And that's it. The theorem is proved. And so previous video 26 is the workhorse of this, and the fact that we can develop it in an equivalent model, which then unfolds to the weighted least squares estimate of beta. Next theorem is this. So we have this linear combination of the least squares estimates, or the weighted least squares estimates for beta. And it equals this. And I have this in parentheses and quotes for two reasons. One is we don't need to use estimability directly to prove this, but I often see this theorem written, if this linear combination is estimable, then the variance equals this. So we're going to do two proofs, one where we don't use estimability directly, and then the next proof we do. So the first one is we're not going to use estimability directly. So the variance of this linear combination is this. So that is the weighted least squares estimate for beta, which is what this is. Okay. So then to find this variance, the only variable is Y. So all this stuff here comes out, and then it comes out back transposed. And that's what this next step is. So this is coming out front, and then this is the transposed of this. But then the variance of Y is sigma squared V. And the sigma squared is a constant, so it can actually come out front. And then the V and V inverse cancel, making the identity matrix. So then what's left over is this. So this comes down, V, this X, and this. Okay. So now this is almost a property of a generalized inverse. Now here it's the generalized inverse, that matrix, the generalized inverse. And that's actually not the definition of a generalized inverse. It's close. It's the definition of what's called a one inverse, is it's actually the matrix generalized inverse times the matrix is equal to the matrix itself. So this is kind of opposite. But there's a video that I put out called Generalized Inverse for a Symmetric Matrix. And this is symmetric, this matrix. And so then it actually becomes what's called a 1-2 generalized inverse, a 1-2 verse of the generalized inverse. And then this is actually equal to just this generalized inverse. And this video here kind of makes reference to that. Well, and then we're done. That's the proof that it equals this. Now the next proof, we use estimability in the proof. And that's, so here we let A be the hat matrix, which is defined as this, be the hat matrix. See previous video 51 in this playlist. General linear models regression is the playlist. So A is an oblique projection matrix onto the column space of X. And we prove it in PV 51. And so that means AX is equal to X. So anything in the column space of X pre-multiplied by this oblique projection matrix projects it back down into itself. But notice if we take the transpose of both of these, it's also true. And then one more note before we jump into the proof is that AVA is equal to this. So here we write out what A is, and then we leave V and A transpose by itself. Well, this is the invert, they're inverses, so that's the identity, and we're left with this. But X transpose A transpose is just X transpose, right? So we put that back in. And then we multiply it by the identity matrix, which doesn't change it. But then this piece here is what we were calling A, and then this is V. So AV, A transpose is equal just to AV. Now let's go to the proof. So let's let the variance of this linear combination of our weighted least squares estimates of beta is equal to this, because L, this vector L can be represented as T prime X. That's because it's estimable. So then the X beta hat is actually A times Y. That's the least squares estimate, and that's what this represents. So then we take this out front and then we transpose it out back. That's what we get here. And the variance of Y is sigma squared V. So the sigma squared comes out front, we have V. But we just showed that AV A transpose is just AV, which is this. Now if we expand what A is, which is this piece here, then the V's cancel, because it's the identity matrix. And then we're left with just this, the variance. And that's what we wanted to show. Well, that's all I have for this video. We have 3 more videos in the weighted least squares regression setting, and then we'll move on to something else. Hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.